Hi, I'm Albert, and we are Las Paletas.
Matthew Aguilar,
Alex Soto,
Michael Clayton.
Alfredo Carvalho.
and I'm going to start off by talking about the Rutherford gold foil experiment. In this experiment, he hypothesized that when he shot particles into a gold foil, that the particles would go straight through and none of them would come back. Little did he know, to his surprise, the particles bounced off the nucleus, and when they did that, they came back, and his hypothesis was proven wrong, and he found out that particles do bounce off the nucleus. Over here we have our stoichiometry. Essentially you're just converting things to moles, and as it says here, the amount of the reactant before the reaction, and then the leftover reactant and the amount of the product after. So it's just this whole process, and you get this end result right here. And then over here we have the states of matter. We have solid right here. Solid, typically the particles are tightly compact. And an example of a solid would be like a rock or your laptop or yourself. Liquids typically have more loosely particles, but they retain their volume. And water is your basic one that would be a liquid. And then for gases, you have helium, you have oxygen, and all of these are particles that move loosely within themselves, but they don't have a definite volume. And then plasma, of course, that's our sun. We don't really come across plasma that often.
All right, on dilution. So if you ever woken up in the morning and you decided to stop by Starbucks and get you a cup of coffee, and if you're the kind of person like sugar in the coffee, you have done dilution. Or even if you just poured salt into water for no apparent reason, you've done dilution. During dilution, water molecules, if you're using water molecules, which is a polar molecule, they have the ability to attract different parts of a substance because of its bent molecular structure. So since it's bent, the positive hydrogen attracts to the negative chlorine. We're using salt as an example, which is sodium chloride. So the positive hydrogen attract the chlorine, and they surround the chlorine to where they totally separate it from the actual object. And then the oxygen, which has a negative charge, attracts the positive sodium ion, which surrounds that and separates that. So pretty much it just does that over and over again until it completely dissipates the actual salt structure. So on to pressure. Pressure with a gas pressure. So with molecules in a gas, there's a lot of kinetic energy, which is motion, just molecules moving randomly throughout everywhere, even in this room, to where right now there's air molecules bouncing off all these walls and generating the pressure. So when the molecules hit the walls, that's the actual pressure, to where it exchanges the energy into the wall, and when you blow up a balloon or a pool or something, it actually expands it. So to explain and use to calculate how a gas will react, we use the ideal gas law. An ideal gas is a gas to where we assume it's all the same molecules, to where there's no difference in the molecules. So we're using this equation. If you held one of these constant, P for pressure, V for volume, N for the amount of the substance, R, which is the constant, and then T is temperature. So N and R normally stay constant, but if T were held constant and P were to increase, the volume would decrease. It would decrease. I'm sorry. And if the pressure was constant and the temperature raised or the volume changed, then they would correlate the same way. And that's pretty much all I have to say.
And I'm going to cover chapters 7 and 6, but we're going to start with 7, which is about quantum theory. And to give you more of a textbook definition, I'm going to go off this little card right here. Quantum mechanics examines the wave nature of objects in the atomic scale. Describes an atom frequency of its electron wave-like motion. So basically it's the position of where electrons can be given within a certain probability of its shape. And so we kind of organize it with these quantum numbers. N would represent any number of s on the periodic table, which would be your first two group elements, and it would range from 0 to 7. If it was 0, it would just have this kind of orbital, which is an s orbital. However, if it's something other than 0, then we look to L, quantum number L, and based on whether it's 1, 2, or 3, we would get p orbital, d orbital, or an f orbital. In some cases, you get a g orbital for L value of 4, but, you know, it's pretty complicated from there, so we don't need to get into that. And then we also have ML, which is the orientation in space, basically where the electrons would most likely be throughout an atom. And then MS is the electron spin, so depending on whether it's, you know, negative 1/2 or positive 1/2, it'll be either counterclockwise or clockwise. And that pretty much is a simplified version of the quantum theory. And now we're going to move to chapter 6, which covers chemical and physical change. For my example, to go over this, we use a thunderstorm because we have both chemical and physical changes happening. For chemical change, we have this lightning, which is packed with high energy. And with these low energy molecules like O2 and N2, once they absorb that high energy, they then go from a low energy molecule to a high energy NO. And that would be an example of chemical change. For physical change, we have all this high energy water vapor. That's a gas right now. And so once it condenses enough, it has enough weight to then become a low energy water vapor, which is basically just rain trickling down. And that is 7 and 6.
So basically, I'm covering electron configuration, which is basically the distribution of electrons around an atom or ion. So basically where they are found around an atom or ion. And basically that instills exactly where the orbitals are around it. And they can actually be found through ionization energy, which is basically how much energy is actually needed to take an electron away from an atom. And that can be quantified through Coulomb's law, which is basically the forces between static electric charges. And that, using Coulomb's law, it can basically start from the inside of an atom to the outside of an atom. And here I have a chart showing the ionization energy. It goes from bottom left to the top right. And if you wanted to find like element ionization energy like boron, it would be 1s, 2s, 2, 2p1. And that's basically how you find electron configuration. And now moving on to ionic bonding, which is basically the bonding between a nonmetal and a metal. And when they actually form a bond, it makes an ionic solid. And that ionic solid actually forms a cation and an anion because it's a transfer of an electron. And an ionic solid is effectively held together, basically is based on Coulomb's law. Okay, and then moving on to a metallic bond, which is basically a group of metallic atoms, and basically the electrons are delocalized. And this is basically set up by the electron C model. And with the electron C model, the electrons that are delocalized have the freedom to move around all over the metallic solid. Now.
Now what we have here is we're going to be speaking about the Lewis dot structures. And basically what this is, it's actually a visual representation of what the molecules would look like. Now what we have here is NO3 minus, and right here we have the resonance structures actually, and these are all correct forms of NO3 minus. However, the bonding and the lone electrons are actually shown differently. As I said earlier, these are all correct still, it's just different ways to write them to better fit the situation. And in order to actually find these, whichever one it is, you would need to experiment. Now right here we have actually hybridization, and basically the main idea of hybridization is taking two orbitals and combining them together to form one. Now right here for an example, we're using methane CH4, and what we have here is the 2s and the 2p orbitals right here. And now in order to hybridize them, we'll combine them and bring these 4 electrons right here all into one category, and they'll bring them to the sp3 orbital. and this combines together, and these type of bonds are either going to be sigma or pi bonds. Now, this all falls under the main idea of valence bond theory, which generally explains just chemical bonding in total. And that's just a summarization of what hybridization is.
And this is the Las Paletas. Thank you guys for your time.
Thank you.
Thank you. We might not be here around for long with our new current president,